In today's lesson, we are going to be looking at sum of squares, or as you might also have heard of it or know it as, Pythagorean theorem. So the reason that we call it sum of squares now is because we've come to realize that Pythagoras, who Pythagorean theorem was named after, wasn't the initial person who came up with this concept. So he definitely did have contributions to the formula, to the theorem, but he wasn't the first one to come up with it. There were actually mathematicians um, looking at right angle triangles and the associated sides. They were looking at that before Pythagoras himself. So we call it sum of squares just to acknowledge that there were many people that contributed to this idea, not just one person. So there are a couple YouTube, or not a couple, there's many YouTube videos. If you want to take a look at these two, one's how to prove the Pythagorean theorem, and the other one is who is Pythagoras, or Pythagoras, the mathematician who started a cult, because he has some interesting thoughts, but he definitely started a cult based off of some of his beliefs. So it's kind of interesting to learn about. But what we're going to look at is sum of squares. So one of the things he had contributions to. And take a look at the two triangles below. What do you notice? What is the same and what is different? Well, you might say that all their sides are different, right? 5, 4, 3, 6, 7, 2. Right? They have a long side and two shorter sides. They're both triangles. You might notice that one has a right angle, right? So one's a right triangle, one's another triangle. Name of a triangle with all three sides being different is escaping me right now. But we have a right triangle, we have a non-right triangle. Now let's change it up a bit. What do you notice now? Some things you might notice is that we've created squares off of each side, and we've done so by basically just taking each measurement, squaring it. So 4 squared is 16. 9 squared is 3 squared. 25 is 5 squared. And the same thing with the other triangle. So we've made squares off of each side. What do we notice about the squares? If you take a look at them, you might notice that this measurement and this measurement equal this. So 16 plus 9 equal 25. But in the other one, if we look over here, 36 and 4 does not equal 49. So in one, the two smaller sides squared add up to the larger side squared. In the other, they don't add up. And this is the relationship that we are looking at with the right angle triangle, which is what sum of squares is. So sum of squares, basically any triangle with a 90-degree angle has two side lengths that when squared add up to the third length squared. If this is not true, then the angle connecting the first two sides must not be 90 degrees. So here we see the example, 4 squared plus 3 squared equals 5 squared. We see the math over here, and it works out, so it is a right angle, or a right angle triangle. If I look at the other triangle, right, we see that they're not equal, or they don't add up to the third side squared. So this is not a right triangle. Now, when we want to look at sum of squares, we want to make sure that we label our sides correctly. So there are a couple things we want to take into consideration, or at least remember. Right? Looking at the triangle, right, it should have a 90-degree angle, which tells us that it's a right triangle. Now, in some cases, we may be using this formula or using this theorem to check if it's a right triangle, but if we're using it in other ways, it should be a right triangle. The other thing we have to label, one is what we call the hypotenuse, which is what we call the longest side. So the longest side of the triangle is this diagonal. It's always going to be called the hypotenuse. If we can't see it or if we can't find it, just because for whatever reason, maybe the way it's angled, the way it's drawn, whatever the case may be, it's always going to be across from 90 degrees. Right? So that right angle triangle, or that hypotenuse, is always going to be across from 90 degrees. The other things we have to label, the two other sides, they actually have the same name, and they're called legs. So one leg, another leg, and they're the two sides that form the 90-degree angle. So the two sides form the 90-degree angle, are called the legs. And we want to know what they are because in our formula, which is a squared plus b squared equals c squared, c is always going to represent the hypotenuse. B and A are going to represent the legs. Doesn't matter which one's which, they're interchangeable, but the hypotenuse is always going to be C. And the formula we're going to be looking at, we're using is a squared plus b squared equals c squared. So the first thing we can do with this is test to see if, given the side lengths of a triangle, is it a right triangle? So here I'm told 5, 12, and 13 are the side lengths, and I want to verify that it is a right triangle. So I'm just going to hypothetically sketch a right triangle. I'm going to place the side lengths 5, 12, and 13. Again, remembering that the longest side is always going to be, or should be, the hypotenuse. So it's going to cross from 90 degrees. And I'm going to write out my formula. A squared plus b squared equals c squared. A and b don't matter as long as they're one of these two. So a and b, I could switch it. And then c has to be the hypotenuse. So 5 squared plus 12 squared equals 13 squared. 25 plus 144. Remember, squared means the number times itself, not times 2 or plus itself. 13 times 13 is 169. And I get that 169 equals 169. So because they both equal the same thing, this means therefore it is a right triangle. So what I want you to do is I want you to go through and do the same thing with these side lengths. So take these side lengths and test to see if they are right, if they make a right triangle. I'm going to pause the video, or I'd recommend you pause the video so you can go and try these on your own, and then we'll come back with the answers and see what we got and see which ones are right triangles. So coming back, we should see that the first one and the last one are not right angled triangles, and the middle two are. One thing to note, there was kind of a mix-up, right? Not a mix-up, but kind of a tricky part. Looking at the third one, right, make sure you label the sides correctly. All the other ones were A, B, and C, or B, A, and then C, but the idea was that last value was always the longest one. In this third one, they were mixed up, so make sure when you are plugging it in that C squared represents the longest side. Right? And when we're given all three sides, that is very important because we are checking basically to see if the sides work with the sum of squares to verify that it's a right triangle. The other thing that we can do is we can find missing side lengths. And if we know two sides of the right triangle, we can substitute it into the formula and solve for the third side. So just remember that A and B always represent the legs, or the short side, and C always represents the hypotenuse. Right? Diagrams sometimes use different letters though. So just make sure you're aware of what sides they represent. Not always A, B, and C. Right? In our formula, yes, but they might be labeled differently on our triangle. So finding side lengths, we want to find the missing one. It's labeled C, which works because it is the hypotenuse. Right? It is the hypotenuse, so C is fine. I want to label the other two. Again, it doesn't really matter. It could be A and B, B and A. It's not going to change our answer. So I'm going to write out my formula. A squared plus B squared equals C squared. 20 squared plus 21 squared equals C squared. 400 plus 441 equals C squared. 841 equals C squared. And you might say, oh, well, I am done. Right? That missing side length is 841. Now, looking at it, you might say, okay, well, this is pretty big. Right? Based on the other two, this is pretty big. And you'd be correct. Right? So there's one last step that we have to do. We do have to square root both sides to get C by itself. I don't want C squared, I want C. So I have to square root 841, and I get 29 is equal to C. So therefore, my missing side length is 29. Now, the other scenario is if we're asked to find another side that is not our hypotenuse. We have it labeled as B, which is fine because it's one of the legs. That means the other side will label A, and then our hypotenuse, which is across from the 90 degree, or the longest side, is C. I'm going to write out my formula. A squared plus B squared equals C squared. I'm going to fill in my information. 24 squared plus B squared equals 30 squared. 24 squared is 576. B squared we don't know, equals 900. Now I'm going to go through and solve this equation, right? Or my goal is to solve this equation for B. So what I have to do is I have to move the 576 over to the other side. Or you can think of it as canceling out, whichever way you want to think of solving it. So if I move the 576 over, it becomes subtraction. 900 minus 576 is 324. So again, I need to get B by itself. So I need to square root both sides. One side cancels out. I get B is equal to the square root of 324, which is 18. So I get that that missing side length is 18. Now looking at it, I can say, okay, does this make sense? And yes, it does, because it is smaller than the hypotenuse. I don't know for sure which one is going to be the larger of A and B, right? Based off the diagram, if it's drawn to scale, then yes, B should be smaller. But the main thing is the legs are smaller than the hypotenuse. So just by looking at the answer, I know I might have done something right, or I should have done something right, because it is smaller than 30. The last question, more of a word problem. So an extension ladder is 6 meters long. It is placed against a wall so that the bottom of the ladder is 1.5 meters from the base. How far up the wall does the ladder reach? So I'm just going to draw my wall and draw my ladder that it goes up the wall, up a certain height, and it is so far away from the ground. I'm going to redraw my ladder. But again, we're not winning art contests. The idea is just that we kind of visually see our triangle. And we can kind of see it here, right? The wall and the ground will form a 90-degree angle. We can assume that they form. And we can place some of our information. We know that it is 1.5 meters from the base and it's 6 meters long, the ladder. And we're asked to find the height, or how far up the wall is our ladder. So now I have enough information. Right? I can see the right angle triangle. I have the hypotenuse, or the ladder, the diagonal, and I'm missing one of the legs. So I'm going to plug in my formula. A squared plus B squared equals C squared. Again, it doesn't really matter which one I label A and B. We can call this A and this B, as long as the hypotenuse is C. So 1.5 squared plus 6, or no, not 6, plus B squared equals 6 squared. 1.5 squared is 2.25 plus b squared equals 36. Again, I want to move the 225 over. I get b squared is equal to 36 minus 2.25, which is 33.75. And then I need to square root both sides. I get that b is equal to 5.8. So that means that the ladder is therefore the ladder reaches 5.8 meters up the wall. So that is like basically an example of the word problem. The main idea is just being able to draw the triangle, and then you can use the sum of squares formula to come up with the missing side length. Again, there's only two scenarios that you'll have. It's either finding a missing leg or finding a hypotenuse. And so we have examples of both. But again, I think from this sometimes gets covered in grade 8. If not, it is really one formula and you're plugging values in and solving equations, which we have spent a whole unit doing. So we should be relatively familiar with that.